Welcome to the Deep Dive, your shortcut to being well-informed, packed with surprising facts and just enough humor to keep you hooked. Today, we're plunging into one of humanity's grandest questions. Are we alone? We're embarking on an incredible deep dive into the scientific quest for life beyond Earth. For this journey, we've pulled together a pretty rich stack of sources, from cutting-edge research to our own distilled notes. And these basically lay out the current scientific understanding of where and how life might exist out there in the cosmos. Our mission today is to extract the most crucial insights from all this material. We want to help you grasp the foundational science and the mind-bending discoveries that are fundamentally reshaping our search for alien life. We'll explore how our very definition of habitable has dramatically expanded, what potential homes for life exist right in our own cosmic backyard, what far-off exoplanets are whispering to us, and the profound questions that anchor this entire quest.
It truly is a pivotal moment in astrobiology. It really is. What was once largely, let's say, philosophical speculation has rapidly matured into a rigorous, data-driven science.
Right. It feels like it's moving so fast now.
Absolutely. Our understanding of life's cosmic potential has truly soared, shifting from a very Earth-centric view of where life can thrive to a far broader, much more inclusive perspective on habitability across the universe.
Okay, let's unpack this. You just mentioned our understanding of life's potential has soared. But before we get to the really exotic stuff, let's nail down the absolute basics. From Earth, what are those non-negotiable requirements we generally look for? And have any of those core ideas been challenged recently?
Well, based on the only example we have right here, life as we know it fundamentally needs three things: liquid water, an energy source, and specific chemical building blocks or nutrients. Liquid water is, it's paramount. It's an incredible solvent, allowing the complex chemical reactions that drive metabolism to happen.
So it lets things mix and react.
Exactly. It dissolves nutrients, transports chemicals around, helps build cell structures like membranes, and gets rid of waste. And crucially, water's unique ability to absorb and release a lot of heat without drastically changing its own temperature. Its thermal buffering property helps stabilize environments. That's vital for sustained life.
Okay, water makes sense. What about energy? I usually think sunshine, photosynthesis.
Right, and that's huge on Earth, obviously. But a groundbreaking discovery in the late 20th century completely changed this view: deep-sea hydrothermal vents. These ecosystems, hidden deep in the lightless ocean, they're powered by chemosynthesis.
Chemosynthesis, so chemical energy.
Precisely. Organisms use chemical energy from inorganic compounds like hydrogen sulfide and molecular hydrogen spewing from the planet's interior. The profound insight here: stellar proximity isn't the only source of energy. This opens up massive possibilities for icy moons far from their stars.
Wow, okay, so water, energy. What about the building blocks?
Right, the nutrients. We're talking about the CHNOPS elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These make up over 98% of living matter on Earth. Carbon is especially vital.
Because it forms chains.
Exactly. Those long, intricate molecular chains that are the backbone of all known life. Of course, other trace elements are also essential for various biochemical processes, things like molybdenum, nickel, zinc.
So given those fundamental needs, water, energy, CH and OPS, what does this mean for the Goldilocks zones beyond Earth? Has our idea of a habitable zone broadened beyond just that sweet spot?
Yeah, it really has. The classical definition of the circumstellar habitable zone, or CHZ, is indeed that Goldilocks zone, the orbital region around a star where a planet could sustain liquid water on its surface. Earth is certainly cozy in our sun's CHZ.
But it's not the whole story.
No, definitely not.
We've realized being in the CHZ is necessary but not sufficient. A planet also needs a stable atmosphere with enough pressure and, crucially, greenhouse gases to actually trap heat and keep that water liquid. And here's where it gets really interesting. Many planets around red dwarfs, which are the most common stars, might actually be uninhabitable.
Why is that?
Well, these stars are prone to powerful flares, really intense bursts of radiation. They can completely strip away atmospheres and basically sterilize a planet. So location isn't everything.
Ah, okay. So the star itself matters hugely.
Hugely. But the truly exciting development is how dramatically our idea of habitable has expanded beyond this traditional Goldilocks definition. Look at the strong evidence for vast subsurface oceans on icy moons like Europa and Enceladus.
Right, under the ice.
Exactly. Kept liquid by tidal forces from their gas giants Jupiter and Saturn. This shows us that liquid water doesn't need to be on the surface or depend directly on stellar energy. It effectively frees liquid water from needing a star's direct warmth.
That's a huge shift in thinking. It is. And we also have theoretical concepts like Hyson worlds. Imagine giant planets mostly made of water, wrapped in a thick hydrogen atmosphere. These could create their own greenhouse effect far from their stars, supporting liquid water much farther out. That significantly widens what we might call the Hyson habitable zone.
So it's not just about where a planet is, but what's happening on or inside it.
Precisely. This entire shift forces a fundamental change in thinking, from a strictly location-based definition of habitability to a more flexible, process-based one.
This expansion of habitable leads us perfectly to Earth's own extreme environments. It almost makes you wonder if our definition of extreme is really just our comfortable Earth-centric bias, doesn't it? What are some of the most surprising environments here that have completely reshaped our thinking about where life could exist beyond Earth?
Oh, absolutely. Extremophiles, these organisms that thrive in conditions once thought universally lethal, they aren't just biological curiosities. They've fundamentally rewritten our rulebook for where life can exist. The profound insight here is that life isn't fragile, it's incredibly tenacious. It shows we must look beyond just Earth-like environments.
Where do we find them?
Well, pretty much everywhere we look, if the conditions are extreme. You have thermophiles and hyperthermophiles in boiling hot springs and deep-sea vents. Some live above water's boiling point. Psychrophiles love the intense cold of polar ice and glaciers. Acidophiles and alkalophiles flourish in highly acidic or alkaline waters.
Like battery acid almost.
Some are close, yeah. Then you have halophiles that need extremely high salt concentrations to survive. And pienzophiles, organisms that thrive under the crushing deep-sea pressures found miles down in the ocean.
Okay, pressure, temperature, acid, salt.
What else? There's radiation resistance. Radioresistance, like the amazing Deinococcus radiodurans, can survive radiation doses that would kill anything else we know. And finally, endoliths, which literally live inside rocks, feeding off minerals, just scraping by in solid rock.
Inside rocks, that's incredible.
It really is. And the existence of these organisms is a cornerstone of modern astrobiology. It provides direct, empirical evidence that the physical and chemical envelopes for life are vastly wider than our everyday experience suggests. This has direct implications for space missions.
How so?
Well, take Europa. The hypothesis that its dark, cold, high-pressure subsurface ocean could harbor life isn't just wild speculation anymore. The fact that we have psychrophiles, piezophiles, and chemotrophs right here on Earth transforms that philosophical question into a testable scientific hypothesis.
It gives us analogs, models for what could be there.
Exactly. And polyextremophile, organisms that handle multiple extremes at once, like those in the Atacama Desert, a key Mars analog environment, they really drive home how remarkably resilient life can be.
That's a fantastic point about life rewriting its own rulebook. So with this expanded definition of habitability, fueled by extremophiles, where are we actually looking for life right now in our own cosmic backyard?
Well, Mars is a primary target, definitely. But it's more of a forensic investigation, you could say. We're looking into a potential lost biosphere. Ancient Mars was undoubtedly warmer and wetter. We see clear evidence of rivers, valleys, lakes like Jezero Crater, where the Perseverance rover is right now.
So the conditions were right once.
The basic ingredients for life as we know it were certainly present. Abundant water, solar energy, volcanic energy, and the CHNOPS elements. The Curiosity rover at Gale Crater even confirmed things like low acidity and chemical energy sources in Mars's past environment.
And we found organic molecules there too, right? That sounds promising.
We have, and that's where it gets tantalizing, but also tricky. Curiosity found total organic carbon in 3.5 billion-year-old mudstone. The concentrations were actually comparable to some of Earth's most life-starved environments, like the Atacama. More recently, evidence suggests even more complex organic molecules, with carbon chains resembling fatty acids up to maybe 12 atoms long.
Okay, but organics don't automatically mean life, do they?
Exactly. That's the critical point, what we sometimes call the organic conundrum. Finding these carbon-based molecules on Mars is, well, it's like finding lumber and bricks at a construction site. They are the ingredients for a house, but it doesn't necessarily prove someone actually built one there. Abiotic processes, things like meteorites delivering organics or volcanic activity or even atmospheric chemistry can create them too.
So finding organics is a necessary step, but not sufficient proof.
Precisely. The real takeaway is that our search must now move beyond merely finding ingredients. We need to identify undeniable biological blueprints or those smoking guns complex structures or chemical patterns that only life, as far as we understand it, can produce. That's the goal for things like Mars sample return.
So while Mars is a fascinating forensic investigation into past habitability, maybe even past life, it's really a cold case for now in terms of active life. If we're talking about searching for active present-day life in our solar system, our attention turns to entirely different, perhaps more dynamic worlds. Which ones are those?
Right. For extant or present-day life, we're looking very hard at the ocean worlds, primarily Europa, one of Jupiter's moons, and Enceladus, one of Saturn's. These are incredibly compelling targets driven by internal heat, not sunlight. Europa is, well, immensely promising. It's widely believed to have a vast, global, liquid saltwater ocean beneath its miles-thick ice shell.
How do we know? Or how confident are we?
Pretty confident. Evidence like the Galileo spacecraft detecting an induced magnetic field that strongly implies a global conductive layer like salty water. And the surface fractures, the chaotic terrain, it all suggests a dynamic ice shell floating on something liquid. This ocean is estimated to hold maybe twice the volume of all of Earth's oceans combined.
Twice Earth's oceans. Wow. And the ingredients?
They seem to be there. The ocean itself provides the liquid water. Tidal flexing from Jupiter's immense gravity constantly needs the moon's interior, generating heat that's the energy source, possibly driving active hydrothermal vents on the ocean floor. Plus, Jupiter's intense radiation bombards the surface ice, splitting water molecules into oxidants, which could potentially cycle down into the ocean and provide a secondary chemical energy source. And the essential CHNOPS elements are likely available from water interacting with a rocky mantle below the ocean.
Okay, Europa sounds amazing, but maybe hard to get to that ocean. What about Enceladus?
Enceladus, yeah. One of Saturn's smaller moons, but in some ways even more exciting right now because the evidence for its ocean is definitive and spectacular and accessible. The Cassini mission actually flew through plumes of icy particles erupting from cracks near its south pole, these tiger stripes. It directly sampled the material coming out from the subsurface ocean.
So it basically tasted the ocean.
In a way, yes. It was like a sample return mission without even needing to land. Analysis confirmed liquid water, various organic molecules, including complex ones, salts, and crucially, molecular hydrogen, H2. The presence of that molecular hydrogen is considered a potential smoking gun.
Why hydrogen specifically?
Because on Earth, molecular hydrogen is a key product of hydrothermal activity of water reacting with hot rock. And it's a fantastic food source for certain types of microbes, particularly those that produce methane, known as methanogens. Finding H2 in the plumes strongly suggests ongoing hydrothermal activity on Enceladus' seafloor, providing both energy and nutrients, analogous to processes powering deep-sea vent ecosystems right here.
And you said it's more accessible.
Arguably, yes. Because the ocean material is actively venting into space, a future mission could potentially fly through the plumes again, perhaps with more advanced instruments designed specifically for life detection, without the immense challenge of drilling through miles of ice like on Europa. That makes Enceladus a very tractable target.
Okay, so Europa and Enceladus represent incredibly exciting possibilities for life as we know it, water-based, maybe powered by chemistry rather than light. But what about something truly wild, something that completely upends our assumptions about life? Where are we looking for life as we truly don't know it, and what would that even look like?
Now you're talking about Titan, Saturn's largest moon. Titan presents a radical possibility that completely challenges our water-centric view of biology. Its surface has stable bodies of liquid, we know this from the Cassini-Huygens mission, but they aren't lakes of water. They're lakes and seas of liquid methane and ethane.
Liquid methane, like natural gas, but liquid.
Exactly. At incredibly frigid temperatures, around minus 179 degrees Celsius or minus 290 Fahrenheit. Despite the extreme cold, Titan is chemically extraordinary. It has a thick, nitrogen-rich atmosphere, much denser than Earth's. It has a methane weather cycle, methane clouds, methane rain, carving river channels into the icy landscape. And the surface gets coated in these complex organic molecules called tholins.
Tholins?
Yeah, it's basically a reddish-brown organic-rich smog or haze that forms from complex chemical reactions high in the atmosphere, driven by sunlight and Saturn's magnetic field. This stuff rains down, coating the surface. Think of it as a ready-made supply of complex organic building blocks constantly being delivered. Lab experiments simulating Titan's conditions have successfully produced all 5 nucleotide bases, the building blocks of DNA and RNA plus amino acids. It's a unique natural laboratory for prebiotic chemistry.
So even if it's too cold for water-based life, maybe something else.
That's the tantalizing question. Titan might offer 2 profoundly different potential habitats. First, like Europa and Enceladus, there's almost certainly a subsurface water ocean, hidden deep beneath its icy crust. Life there, if it exists, would likely be life as we know it, water-based. But the truly revolutionary possibility is surface life, existing in those liquid methane lakes, life as we don't know it.
How could that even work? Life based on methane?
Well, it's highly speculative, of course, but scientists have explored theoretical concepts. For instance, instead of a lipid bilayer membrane like our cells use in water, maybe life in methane could use something called an azotosome. It's a theoretical structure made from small nitrogen-containing organic molecules, like acrylonitrile, which calculations suggest could self-assemble into flexible, stable, membrane-like spheres in liquid methane.
A completely different kind of cell wall.
Potentially. And a proposed metabolism could involve organisms consuming hydrogen gas, which is scarce in Titan's atmosphere, and acetylene, which is abundant on the surface, and reacting them to produce methane, releasing energy in the process. It's chemically plausible. Finding such weird life on Titan would be absolutely staggering.
It would change everything.
Completely. It would suggest that life isn't just a fluke tied to Earth's specific water and carbon chemistry, but maybe a more fundamental cosmic process that adapts to whatever local conditions and solvents are available.
So if we compare these worlds, Earth has surface liquid water, Mars had it, might have subsurface right now, Europa, Enceladus subsurface liquid water oceans, and Titan, surface liquid methane, ethane, plus maybe that deep water ocean too.
Exactly. And their energy sources range from sunlight for Earth and ancient Mars to primarily tidal forces and chemical energy for the ocean worlds, maybe some atmospheric chemistry for Titan's surface. The organic chemistry is wildly different too. Each place poses a unique, fundamental astrobiological question from did life ever exist on Mars to does life exist now in hidden oceans to can life exist without liquid water at all?
It's incredible how much potential variety there is just within our own solar system. But let's broaden our view now. We've explored the neighborhood, but what's out there, far beyond our solar system? How are we even beginning to look for life on those distant worlds, these exoplanets?
Yeah, the discovery of, well, thousands of exoplanets now has fundamentally reshaped the search for life. It's become a truly galactic endeavor. We've moved beyond just detecting planets to the much harder task of characterizing them. A prime example everyone talks about is the TRAPPIST-1 system.
Yes, the 7 Earth-sized planets.
Exactly, just over 40 light years away, which is practically next door in cosmic terms. 7 Earth-sized rocky planets, and crucially, they all transit their star from our point of view. That means they pass in front of it, which makes them absolutely ideal for atmospheric study.
What kind of star is it?
TRAPPIST-1 itself is an ultra-cool red dwarf star. It's tiny, only about 9% of the sun's mass, much fainter, much redder. These stars are incredibly common in the galaxy, maybe 75% of all stars. And they're incredibly long-lived. They'll burn for trillions of years, offering a vast timescale for life to potentially evolve. But there's a catch.
Always a catch.
The flares. The flares. Red dwarfs, especially young ones, can be very volatile, unleashing frequent, powerful flares that, as we discuss, could strip away atmospheres and bathe the planets in sterilizing radiation. The planets themselves are packed incredibly close together, much closer than Mercury is to our sun. They're almost certainly tidally locked.
Meaning one side always faces the star, a permanent day side and night side.
That's right. Despite orbiting such a dim star, several of them, planets D, E, F, and G, are technically within the star's habitable zone, where surface water could exist if conditions are right. TRAPPIST-1m is often highlighted as the most potentially Earth-like in terms of its size and the amount of stellar energy it receives.
And they might be water worlds?
Some models suggest they could be incredibly water-rich, yes, potentially holding hundreds of times the water of Earth's oceans, maybe making them water worlds with deep global oceans. Or maybe they lost their water early on, we don't know yet. But this system, TRAPPIST-1, it perfectly encapsulates the central astrobiological debate right now. Does the sheer abundance of planets around these very common, long-lived red dwarf stars outweigh the potential environmental hostility of those stars? Is it quantity versus quality, in a sense?
That's a fascinating trade-off. And you mentioned Planet Chi as a prime candidate, but maybe G could be one of those high-seen worlds.
Exactly. Planets B and C are likely too hot, scorched like Venus, perhaps. Planet E gets about the same amount of light as Earth. Planets F and G are further out in the habitable zone, maybe cooler. Perhaps G could sustain a liquid ocean under a hydrogen atmosphere if it has one, a potential Hyson world. It's a natural laboratory for different planetary possibilities.
Okay, but if we can't visit these exoplanets, how do we even begin to look for signs of life? It seems like an impossible task from light years away.
It is a huge challenge, absolutely. So we rely on remote detection, specifically by looking for biosignatures. These are measurable properties, could be chemical, physical, that provide scientific evidence suggesting the presence of life. The most actively pursued type right now are gaseous biosignatures. The idea is that life, especially widespread life, fundamentally alters a planet's atmosphere in detectable ways.
Like on Earth.
Exactly like Earth. Our atmosphere is wildly out of chemical equilibrium. The most powerful example is the coexistence of large amounts of oxygen, O2, and methane, CH4. Chemically, these two gases should react quickly and destroy each other. Their persistent presence at high levels means something is constantly producing both of them. And that something is life photosynthesis making oxygen, methanogens making methane.
So finding oxygen and methane together on an exoplanet would be huge.
It would be incredibly exciting, yes. Other potential gaseous biosignatures include ozone, O3, which is a byproduct of oxygen, nitrous oxide, N2O, also produced by microbes, or maybe ammonia, NH3. We can also think about surface biosignatures. On Earth, the most famous example is the vegetation red edge, or VRE. Plant chlorophyll absorbs strongly invisible light, but reflects very strongly in the near-infrared part of the spectrum. This sharp increase in reflectance is a distinctive signal. Finding something similar on an exoplanet could hint at widespread surface life, maybe some form of alien photosynthesis, or even temporal biosignatures, like seeing seasonal oscillations in atmospheric carbon dioxide, perhaps as alien plants bloom and decay over the year.
Okay, so how do we detect these gases or surface features from so far away?
The primary method right now, especially for gases, is transmission spectroscopy. It relies on those transits we talked about with TRAPPIST-1. When a planet passes in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere on its way to our telescopes. Different molecules in the atmosphere absorb starlight at specific characteristic wavelengths or colors.
Like a chemical fingerprint.
Exactly. By analyzing the starlight that reaches us during the transit and comparing it to the starlight outside the transit, we can see which wavelengths are missing. Those missing slivers tell us which gases are present in the planet's atmosphere and potentially even give us hints about their abundance.
But it can't be that easy, right? Are there pitfalls?
Oh, absolutely. Huge challenges and ambiguities. The biggest one is the problem of false positives. These are abiotic or non-biological processes that can mimic a biosignature. For example, you can generate oxygen without life. Intense ultraviolet radiation from a star can split water molecules in an atmosphere. If the lighter hydrogen escapes to space faster than the oxygen, you could build up an oxygen atmosphere without any biology.
So finding oxygen alone isn't proof.
Definitely not. Context is paramount. Finding oxygen is far more compelling if it's found on a planet that clearly has liquid water on its surface, and especially if it's found coexisting with a reducing gas like methane, that chemical disequilibrium we talked about. Methane itself can also be produced by geological activity, not just life, so scientists have to be incredibly careful. They use complex atmospheric models and statistical methods like Bayesian analysis to weigh all the evidence, consider alternative explanations, and determine how confident they can be that a detected signal is truly biological. It's about building a case, not finding one single magic bullet.
This sounds like where the James Webb Space Telescope comes in. Everyone's talking about the Webb era. How exactly is JWST changing the game here, and what have been its most surprising findings or maybe challenges so far in this search?
The Webb era has absolutely begun, and it is revolutionizing exoplanet atmosphere characterization. Its incredible sensitivity, especially in the infrared part of the spectrum where many molecules have strong absorption features, is just unparalleled. It's already had some stunning early successes. For instance, it produced a really detailed molecular and chemical profile of the atmosphere of a hot gas giant called SP39b. It found clear signs of water, carbon dioxide, carbon monoxide, sodium, potassium.
Things we expected.
Mostly, yes. But it also made the first ever detection of sulfur dioxide, SO2, in an exoplanet atmosphere. Finding SO2 was significant because it's likely produced by photochemistry starlight breaking down other molecules, which tells us about active chemical processes happening high up in that planet's atmosphere. Webb has also pushed the boundaries of directly imaging exoplanets, capturing photos of young gas giants orbiting their stars.
So it's working brilliantly for gas giants.
Yeah.
What about the small, rocky, potentially habitable worlds like the TRAPPIST-1 planets?
That's where it's proven much, much harder. Characterizing the atmospheres of small, rocky, Earth-sized planets is really pushing Webb to its limits. The signals are incredibly tiny. Early observations of some of the TRAPPIST-1 planets and another potentially habitable world called LHS 1140b have been, well, somewhat inconclusive so far. Often the transmission spectra come back looking flat and featureless.
Flat. What does that mean?
It could mean several things, and that's the challenge. It might mean these planets simply don't have substantial atmospheres anymore. Perhaps they were stripped away by their star's activity early on. Or it could mean they have very high-altitude clouds or hazes that are essentially opaque, blocking the starlight from penetrating down to where we could detect gases lower down. Think of trying to see through a thick fog layer. Another possibility is that they have very dense atmospheres, perhaps dominated by heavier gases like CO2, which can mute the spectral features of other molecules if the atmosphere is compact. The general absence of strong carbon dioxide absorption in some of these early results is also puzzling and might suggest these worlds formed with fewer volatile compounds like water and CO2 than we expected, or lost them very quickly.
So we're getting data, but it's hard to interpret.
Exactly. What's emerged, somewhat unexpectedly, is what some scientists are calling an interpretation bottleneck. Webb is delivering data of such unprecedented quality and detail, especially for the more favorable gas giant targets, that our current scientific models and computational tools, the complex simulations we use to understand what the spectra mean, are actually struggling to keep up. Different teams analyzing the same data can sometimes arrive at different conclusions about atmospheric composition or temperature. The key insight here isn't that Webb isn't working. It is spectacularly, but that our ability to decode the subtle messages hidden in the light from these alien atmospheres needs to advance alongside the hardware. We need better models for 3D atmospheric circulation, cloud formation, stellar activity effects.
That's a fascinating challenge to have. A good problem, in a way. So this is clearly a long-term quest. Looking ahead, what's next on the roadmap for astrobiology, both in our solar system and beyond?
The future really involves a dual-pronged strategy, pushing forward both with intense close-up investigations within our solar system and with developing the next generation of powerful space telescopes to look further afield. For our solar system, we have two incredibly exciting flagship missions coming up very soon. First is the Europa Clipper. It actually launched in October 2024, and it's scheduled to arrive at Jupiter in April 2030.
Clipper. So it's an orbiter.
Primarily, yes. It's focused on habitability assessment, not direct life detection itself. Its main job is to figure out if Europa really has the conditions suitable for life. It will perform dozens of close flybys of Europa using ice-penetrating radar, an instrument called REASON, to map the thickness of the ice shell and search for pockets of liquid water within or just beneath it. It has a magnetometer to better characterize the ocean's salinity and depth by studying its induced magnetic field, and spectrometers will analyze the surface composition, looking for salts or organic molecules that might have erupted from the ocean below. The ultimate goal is to understand Europa much better and, critically, help select a safe and scientifically interesting landing site for a potential future mission that would search directly for life.
Okay, so Clipper scouts it out. What's the other big one?
That's Dragonfly, scheduled to launch in July 2028 and arrive at Saturn's moon Titan in 2034. This mission is truly revolutionary. Dragonfly is a nuclear-powered octocopter, basically a large drone.
A drone on Titan, how does that work?
Remarkably well, it turns out. Titan's atmosphere is about 4 times denser than Earth's at the surface, and its gravity is only about 1/7 of Earth's. That combination makes powered flight relatively easy. Dragonfly will be able to fly to dozens of different locations across Titan's surface, potentially covering hundreds of kilometers over its multi-year mission. Its main goals are to investigate Titan's complex prebiotic chemistry, assess its habitability both on the surface and regarding the potential subsurface ocean, and search for chemical biosignatures, perhaps signs of that weird life we talked about. A key target is the Selk impact crater. The idea is that the heat from the impact might have melted the water ice locally, creating a temporary pool of liquid water that could have mixed with Titan's abundant surface organics for thousands of years, a potential crucible for interesting chemistry, maybe even the origins of life.
Flying a nuclear-powered drone on an alien moon. Science fiction becoming reality. What about looking beyond our solar system, beyond Webb?
Right. As powerful as Webb is, it likely won't be able to definitively detect biosignatures on Earth-like planets around Sun-like stars. For that, we need the next generation of great observatories. The community has identified the top priority: a large space telescope designed specifically to directly image potentially Earth-like exoplanets orbiting stars similar to our Sun, and to analyze their atmospheres for biosignatures. This future mission currently goes by the name Habitable Worlds Observatory, or HWO.
HWO. When might we see that?
It's projected for launch sometime in the 2040s, so it's still a couple of decades away, but the planning and technology development are starting now. Its primary goal is ambitious: to directly image about 25 potentially Earth-like exoplanets and obtain detailed spectra of their atmospheres to search for gases like oxygen, water vapor, methane, and others. The major technological challenge is suppressing the blinding light from the host star itself.
Right, the firefly next to the lighthouse problem.
Exactly. The planet is incredibly faint compared to its star, maybe 10 billion times fainter in visible light. HWO will need incredibly advanced technology, likely an internal coronagraph combined with extreme telescope stability, to block out that starlight with exquisite precision, allowing the faint planet's light to be seen and analyzed. HWO is envisioned as roughly a 6-meter aperture telescope, kind of a successor inheriting capabilities from earlier, even more ambitious concepts like LVUR and HABEX that were studied previously.
So HWO is the big one on the horizon. Are there other future telescope ideas?
Yes, there are other concepts being considered too. For example, the Origin Space Telescope, OST, concept focused on the far infrared part of the spectrum. That would be crucial for tracing the journey of water from interstellar clouds to planets, and could also potentially detect certain biosignatures in the mid-infrared. And we shouldn't forget the ground-based telescopes. The next generation of extremely large telescopes, or ELTs, are currently under construction. ESO's ELT in Chile will have a primary mirror nearly 39 meters across. The Giant Magellan Telescope, GMT, will be about 25 meters.
39 meters. That's enormous.
It's staggering. Equipped with sophisticated adaptive optics systems to counteract the blurring effects of Earth's atmosphere, these ELTs will have immense power. They'll be able to characterize the atmospheres of some transiting planets, especially those around nearby red dwarfs, in great detail. They'll also be powerful tools for directly imaging young, giant planets that are still glowing hot from their formation. They will beautifully complement the space missions like Webb and eventually HWO. So you see, there's a multi-decade roadmap involving missions in our solar system and increasingly powerful telescopes, taking us from initial discovery towards hopefully definitive searches for life elsewhere.
This entire journey into the unknown, it also forces us to confront some of the biggest questions in science and even philosophy. Let's maybe shift gears slightly and talk about the theoretical side of the search. Where does something like the Drake equation fit in?
The Drake equation. It's famous and often a bit misunderstood. Frank Drake formulated it back in 1961, really as an agenda for a meeting, a way to structure discussion. It's less about getting a precise number for how many civilizations are out there, and more about prompting us to ask the right questions, to identify the key factors involved. As Frank Drake himself often said, it's really just a way to organize our ignorance.
Okay, so what are the factors?
It breaks the question, how many detectable civilizations in our galaxy, down into 7 variables. It starts with R star, the average rate of suitable star formation, then FP, the fraction of those stars that have planets. Next, the average number of planets that can potentially support life per star, with planets essentially, the number of habitable worlds. Those first 3 are basically astronomical terms.
So we have better handles on those now, right? Thanks to Kepler, Webb, etc.
Much better, yes. Decades of astronomical observation have given us reasonably good constraints on R star, FP, and NE. We know planets are common, and potentially habitable worlds might be too. But then comes FL, the fraction of those habitable planets where life actually arises or develops. Then Phi, the fraction of planets with life that go on to develop intelligent life. And FC, the fraction of civilizations with intelligent life that develop technology that releases detectable signs of their existence into space.
That doesn't sound like complete unknowns.
Largely, yes. FEL and Phi are the big biological unknowns. This is exactly what the search for biosignatures is trying to address. Finding any life beyond Earth would start to give us a value for Phala. Finding intelligent life, well, that addresses Phi. And the final term, L, is the length of time for which such civilizations release detectable signals. How long does a technological civilization last?
That one feels particularly uncertain, and maybe a bit sobering.
It is the most speculative and perhaps the most sobering. If civilizations tend to destroy themselves quickly after developing technology, or if they cease broadcasting for other reasons, then L could be very short. Even if civilizations arise frequently, if they don't last long, the chance of detecting one right now would be incredibly small. When you look at the Drake equation variables, the uncertainty is revealing. The astronomical terms, R, F, P, N, have estimates that might vary by factors of, say, 10. But the biological terms, FL, A, Phi, and especially the societal terms, FCL, have uncertainty spanning many, many orders of magnitude from incredibly optimistic to deeply pessimistic. It really highlights where the biggest gaps in our knowledge are.
So if the early terms suggest planets are common, and maybe habitable planets are common, but the later terms are huge question marks, this leads directly to that big paradox, doesn't it? If the galaxy is potentially teeming with life, why haven't we heard from anyone? It feels like a cosmic contradiction.
That is the absolute essence of the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a lunchtime conversation in 1950. It's the stark contradiction between the high probability estimates for extraterrestrial life, especially if you're optimistic about the Drake equation, and the complete lack of observational evidence. The Great Silence, as it's sometimes called, is actually a powerful scientific observation in itself.
Why is the silence so significant?
Because the galaxy is incredibly old, over 13 billion years. Our solar system is only about 4.5 billion years old. That means civilizations could have arisen billions of years before us. Even with relatively slow interstellar travel speeds, much slower than the speed of light, a technological civilization would have had ample time to expand across the galaxy, or at least leave very obvious signs of its presence: large-scale engineering projects, communication signals, probes. The fact that we observe none of this, that Earth apparently hasn't been visited or colonized, is profoundly puzzling if life and intelligence arise easily.
So how do we resolve this paradox? What are the leading ideas?
Well, there are many proposed solutions, but one of the most compelling and perhaps chilling is the Great Filter hypothesis. This hypothesis posits that somewhere along the long evolutionary pathway from the very first non-living molecules to a galaxy-spanning technological civilization, there exists at least one step that is extraordinarily difficult, incredibly improbable, a kind of barrier or filter that almost no species ever manages to overcome.
A bottleneck somewhere in development.
Exactly. The critical question for us then becomes, where is this filter located in the timeline relative to humanity? Option 1 is the filter behind us. This is the optimistic view. It suggests that humanity has already successfully passed the incredibly difficult step. Maybe the origin of life itself, or biogenesis, was the filter, or perhaps the evolution of complex eukaryotic cells, or the development of technological intelligence like ours. If so, it would mean that we are very rare, perhaps even unique, and the future might be open for us to explore the galaxy.
Okay, that's the hopeful scenario. What's the alternative?
The alternative is more ominous, is the filter ahead of us. This suggests that the early steps, formation of planets, origin of life, even development of intelligence, might actually be relatively common. If that's true, then the Great Silence implies that the filter lies in our future. It would be some challenge that consistently prevents civilizations from achieving longevity or interstellar capability. Perhaps it's an inherent tendency towards self-destruction through nuclear war or environmental collapse. Or maybe it's some unknown natural phenomenon that inevitably wipes out advanced life.
That's unsettling. So finding simple life elsewhere might actually be bad news in this context.
Paradoxically, yes, according to the Great Filter logic. If we discovered microbial life on Mars, for instance, something that arose independently from Earth life, it would suggest that the first filter, origin of life, LSL, is not that hard to pass. That would increase the probability that the truly hard filter, the one responsible for the Great Silence, lies further down the evolutionary chain, potentially still ahead of us. It's a very counterintuitive idea.
It really is a sobering thought, the Great Filter. But is it the only explanation? Are there other popular theories for the Great Silence that don't necessarily involve humanity facing some kind of inevitable existential crisis? And maybe more importantly, what does this silence, this paradox, tell us about how we should be looking? Does it guide our search strategy?
That's a great point. The Great Filter is compelling, but certainly not universally accepted. And yes, the paradox absolutely compels us to broaden our search strategies significantly. For one, we need to seriously consider alternative biochemistries and develop what are called agnostic biosignatures. We need to challenge our inherent carbon chauvinism and our focus on water. Could life be based on silicon instead of carbon? Could it use a different solvent, like liquid methane on Titan, or perhaps ammonia? Agnostic biosignatures would be signs of life that are independent of its specific molecular makeup. Instead of looking for specific molecules like oxygen, we'd look for more general signs of complexity, things that seem unlikely to arise through purely geological or chemical processes. Maybe looking for unusual accumulations of certain elements, complex structural patterns, or evidence of large-scale chemical disequilibrium that isn't easily explained.
Looking for weirdness itself is a sign of life.
In a sense, yes. looking for something that screams artificial or complex or unexpectedly ordered without assuming it has to look like Earth life. We also need to dramatically expand our search for technosignatures. This is the modern, broader vision of SETI, the search for extraterrestrial intelligence. It's not just about listening for deliberate radio messages anymore.
What else does searching for technosignatures involve?
It means looking for any measurable evidence of advanced technology. This could still include communications, not just radio, but maybe powerful optical laser signals used for communication or propulsion. It could involve searching for huge megastructures like Dyson spheres or swarms designed to capture stars' energy, perhaps by looking for their waste heat signature in the infrared. It could even involve looking for signs of industrial pollution in an exoplanet's atmosphere, maybe synthetic gases like CFCs that are unlikely to occur naturally, or searching for anomalies like artificial lights on the night side of a planet, constellations of satellites, or even evidence of interstellar spacecraft.
So basically looking for anything that indicates technology, not just biology.
Exactly, broadening the search in every way possible. And finally, there's a simpler, perhaps less dramatic physics-based resolution to the Fermi paradox that doesn't require a great filter at all. And that's simply that interstellar travel and communication are extraordinarily difficult, perhaps practically impossible for sustained, large-scale interaction.
That's too far, too hard.
Essentially, yes. The distances between stars are genuinely incomprehensible. Voyager 1, one of our fastest spacecraft, has been traveling for over 45 years and is just entering interstellar space. It would take it about 75,000 years to reach the nearest star system, Proxima Centauri. The energy required to send even robotic probes, let alone crewed missions, at significant fractions of the speed of light is astronomical, far beyond anything we can currently conceive. Interstellar space itself is hazardous cosmic rays, dust impacts at high speeds. And communication over interstellar distances is incredibly challenging, too. Signals become extremely faint, take years or decades to travel one way, and face various forms of interference. So it's entirely possible that civilizations arise, develop technology, maybe even thrive for long periods, but they remain effectively isolated islands in the vast cosmic ocean, simply unable to cross the gulfs between stars in any meaningful way. This could resolve the Fermi paradox, explaining the Great Silence without needing to invoke a universal filter or impending doom.
That feels less scary somehow. Civilizations might be out there, just too far away to talk to.
It's certainly a plausible alternative. And notice the profound philosophical tension this creates. If we eventually find widespread microbial life, biosignatures, the Great Filter hypothesis might suggest the filter is still ahead of us. But if we were to find evidence of intelligent life or technology, technosignatures, it would be monumental proof that long-term survival and perhaps even interstellar capability are possible, potentially resolving the filter question in a much more optimistic way. The stakes are incredibly high.
What an incredible journey we've just taken. We've gone from the basic requirements for life to the farthest reaches of the cosmos and the deepest philosophical questions. It feels like astrobiology has truly transformed from speculation into a robust, interdisciplinary science. Earth is currently our only example of life, that's still true, but the scientific optimism, the methodology for finding more, seems to be at an all-time high.
That's absolutely right. Our whole definition of habitability has profoundly expanded, hasn't it? It's become so much more about the processes, internal heating, chemical energy, rather than just being in that narrow Goldilocks zone around a star. And that expansion is directly informed by discovering Earth's amazing extremophiles and understanding the potential of these diverse planetary environments we're finding.
And we've seen how this expanded view guides our targets right here in the solar system. Mars' ancient, potentially watery past, Europa and Enceladus's hidden, potentially life-sustaining present-day oceans, and Titan's incredibly weird potential for life as we don't even know it, based in methane perhaps. Plus, the exciting missions like Europa Clipper, already on its way, and Dragonfly, preparing for launch, are poised to investigate these worlds with unprecedented detail in the coming decade.
Exactly. And then beyond our solar system, the exoplanetary frontier is just exploding with possibilities. JWST is giving us these tantalizing, though challenging, first glimpses into distant atmospheres. And the ambitious plans for the next generation, especially the Habitable Worlds Observatory, are specifically designed to take that crucial next step, to directly image potentially Earth-like worlds and analyze their air for signs of life. That really marks a shift from relying on indirect methods towards robust, direct searches for biosignatures.
It all seems to come together, doesn't it? These incredible empirical efforts building the probes, launching the telescopes, are constantly interacting with and being framed by those big theoretical questions like the Drake equation and the Fermi paradox. The Great Silence remains a profound mystery, a powerful observation that continues to push us to explore further, to look harder, and maybe to look differently.
Absolutely. The journey ahead is undeniably long, and the challenges, technological, scientific, financial, are immense. But I think the key takeaway is that really, for the first time in human history, we have a credible, evidence-driven roadmap, a scientific plan, to actually try and answer humanity's oldest, perhaps deepest question: are we alone? So let me turn that back to you, our listener. Thinking about everything we've discussed, the hidden oceans, the weird chemistry of Titan, the distant worlds, the great silence, what do you think is the most exciting or perhaps the most unsettling possibility in this grand search?